In a previous presentation on my YouTube channel titled Fixed Bed Adsorbers Scale-Up Issues, I had highlighted the important differences between the operation of laboratory scale breakthrough experimental apparatus and industrial fixed bed adsorbers. In the laboratory, experiments are carried out in breakthrough tubes of internal diameters approximately 5 to 10 millimeters, packed bed lengths of about 50 millimeters to 100 millimeters, inlet gas flow rates of the order of 1 milliliter per minute to say 5 or 10 milliliters per minute. The superficial gas velocity inside the fixed bed tubes is of the order of 0.2 millimeters per second, and the interstitial gas velocity, that is the superficial gas velocity divided by the bed voidage, is of the order of half a millimeter per second. We determine the contact time between the gas and the morph crystals, that is the length of the packed bed divided by the interstitial gas velocity. This is of the order of 100 seconds or so. Usually we associate diffusional influences with the parameter called the diffusional time constant, that is the ratio of the Maxwell-Stefan diffusivity of component 1 to the square of the crystallite radius. Compare these conditions with those in an industrial fixed bed adsorber. Let's assume that the experiments are carried out with the same pellet diameter. An industrial fixed bed adsorber would be about half a meter, maybe even 2 meters in diameter. The length of the packed bed could be about 5 meters, maybe even 10 meters. Let's say the voidage in the packed beds is approximately 0.5 to 0.6. However, in industrial units, the superficial gas velocity may be significantly higher, about a factor 1,000 higher than in the laboratory scale unit, which means that the contact time between the gas mixture and the pellets or crystals may be an order of magnitude smaller in the industrial fixed bed adsorber than in the laboratory scale unit. Even if the intracrystalline diffusional influences, as quantified by the diffusional time constant, is maintained the same, the diffusional influences are more severe in industrial fixed bed adsorbers because the contact time is about an order of magnitude smaller than in the laboratory. And in today's presentation, I'm going to explore this aspect of contact time and diffusional time constants. To highlight the influences of contact time on the separation performance of fixed bed adsorbers, I consider separations of 50-50 mixtures of propene and propane using chamosite zeolite. The background to the separation is described in detail in my video presentation, Propene-Propane Separations with Chamosite Zeolite. In this presentation, I had stressed the need to adopt the Maxwell-Stefan formulation in PSA modeling by taking due account of thermodynamic coupling effects. Today, I will indeed use the Maxwell-Stefan formulations and take due account of thermodynamic coupling, but focus on the influence on contact times, on separations. For this purpose, I present results for 4 different sets of simulations for a packed bed packed with Chabasite zeolite crystals. The length of the packed bed is 0.3 meters in all 4 cases. The packed bed voidage is 0.4, also maintained the same in all 4 cases. The superficial gas velocity entering the packed bed is varied from 4 millimeters per second, 8 millimeters per second, 20 millimeters per second, and 60 millimeters per second. These correspond to interstitial gas velocities of 10 millimeters per second, 20 millimeters per second, 50 millimeters per second, and 150 millimeters per second. The corresponding values of the contact times, which is the ratio of the packed bed lengths to the interstitial gas velocity, is 30 seconds in the first case, 15 seconds, 6 seconds, and 2 seconds. The diffusional time constant is maintained the same in all 4 cases and equals 1.7 times 10 minus 4 per second. Let's look at the simulation reason. The transient breakthrough data for the 4 sets of simulations are shown here. The diffusional effects are stronger for the case in which the contact time is the shortest, because the penetration of the gas components into the crystals of Chabasite zeolite is shallower if the contact time is smaller. Indeed, if you look at the red curves for a contact time of 2 seconds, we see that the breakthrough of propene occurs earlier, implying that the amount of propane that is recovered in purified form is lower than in the case in which the contact time is the highest. And the blue lines refer to the simulations in which the contact time is 30 seconds. So in the time interval from here to here, purified propane is recovered, whereas for the simulations with a contact time of 2 seconds, the time interval during which purified propane can be recovered is about a factor 5 smaller. Let's consider a different set of simulations, 4 in number, in which the product of the contact time and the diffusional diffusional time constant is maintained the same at a value of 2.55 times 10 minus 3 by having different values of the diffusional time constants, such that the product of the diffusional time constant and the contact time remains the same. The ratio of the Maxwell-Stefan diffusivity is also maintained the same at 5000. In this case, all 4 simulations collapse to yield a single curve. This indicates that the diffusional influences are described by the diffusional time constant times the contact time between the gas and the MOF or zeolite crystals.